Flipped classroom video for Maths AS Unit 1. Combinations, permutations and Pascal's triangle. Subsets of objects. Teams and medals. So, imagine we have 8 athletes and they run a race. How many different outcomes are there if there are gold, silver and bronze medals available for the first 3 to finish? Or imagine instead that we're picking a team of 3 from our set of 8 athletes. Is this the same as the first scenario? Well, let's start with our medals. For gold, any of the 8 athletes can win it. For silver, any of the remaining 7 can win it. And bronze, any of the remaining 6. And this means the total number of possible outcomes for the medals is 8 times 7 times 6. Which happens to be 336. Now, let's imagine that one outcome for the medals is that Ava wins the gold, Bella the silver and Caddy the bronze. But it could have been that Ava won the gold and Caddy the silver and Bella the bronze. And in fact there are 6 possibilities for medal outcomes which would give the same team. So if we were choosing a team of 3, those 2 that we've just looked at would be the same, and in fact there are 4 others. So we've got Ava, Bella, Caddy, Bella, Caddy, Ava, Caddy, Ava, Bella, and so on. So a good way of thinking of this is that from those 3 people, Ava, Bella and Caddy, we've got 3 choices for the first team member, 2 for the second, and then the third is decided for us. And if we look at it on a sort of diagram like that, tree diagram type of thing, then we have 3 choices for the first one. That would be the orange choice, and then we've got 2 choices. Having chosen an orange, then we have the silver choices, and once we've chosen the second one, we've only got 1 choice, and so that gives us our 6 possible outcomes. And this means that the total number of different teams must be the number of possible medal outcomes divided by 6. Because those 336 outcomes we had before come in sets of 6. And each of those sets of 6 have 3 of the athletes. So the one we looked at was Ava, Bella and Caddy. But it could have been Ava, Bella and Delith, or Bella, Caddy and Delith, and so on and so on. So we have to divide that 336 by 6 to find how many different teams there are. And that gives us 56. And thinking of where the numbers actually came from, we have 8 times 7 times 6, which was the number of outcomes for the medals, divided by 3 times 2 times 1, which meant that the combinations of 3 different medalists were not included 6 times but just the once. Okay, so that takes us on to combinations and permutations and shriek. So, what's the difference? The difference between the medal scenario and the team one is that for the medals the order matters. And in that case we're dealing with permutations. So the order matters. It matters whether you get gold or silver or bronze. For the team scenario, the order doesn't matter. If you're in the team, you're in the team. It may matter a little bit at the time if you're being picked, but if the team list goes up and your name's on it, then it doesn't matter what order it is really. And in that case, we're dealing with combinations. And you can find these on your calculator. If you look with the times and the divide buttons, you've got NPR, which is permutations, and MCR, which is combinations. And they can be written in various ways, but the calculator way of writing it is common enough. Also common is NCR with the N as a superscript and the R as a subscript, and also very common is the bracketed version with an N and an R. Looks a little like a vector, and this is used in the WJC formula booklet, for example. And the way we'd find out how many different ways there were for 3 medals from 8 competitors would be using 8 shift times and then 3, so that will give us 8p3, which is then the 336. And for the teams, we'd have 8 shift divide 3, which is 8c3, and that would be 56 as before. We're now going to introduce another mathematical concept, which is shriek, and actually you've probably come across this before. It's generally called factorial. Bang is also used. These are terms that come to some extent from the IT world, and shriek, as I just said, is a synonym for factorial. And the reason we like it, or I like it, is it's one syllable instead of factorial, which is many syllables. So the symbol we use for this is exclamation mark, so n factorial or n shriek equals n exclamation mark, and that is n times by n take away 1 times by n take away 2 all the way down to 3 times 2 times 1. So it's n times by all the whole numbers below it down to 1. So for example, we have 6 shriek is 6 times 5 times 4 times 3 times 2 times 1, which is 720. And on the calculator, we have that as the shift above the reciprocal button, the x to the minus 1 button, and that is x with an exclamation mark. As you can see, that's on the class whiz, of course. If you have a different calculator, you'll still find the factorial or shriek somewhere on it. Okay, combinations as factorials. Well, we have seen already that we can write the number of ways of choosing teams of 3 from 8 players. We've just seen that we can write that as 8c3, but we have seen that the way of calculating that is, or one way of calculating it is 8 times 7 times 6 divided by 3 times 2 times 1. And there's a nice little trick we can use to express this in factorial form. And what we do is we times the top by 5 times 4 times 3 times 2 times 1, and if we times the top of a fraction by something, as long as we times the bottom of it by the same thing, then it stays the same, as you will know. So you can see that we've times the bottom also by 5 times 4 times 3 times 2 times 1, and what that means is on the top we actually now have 8 factorial, because we've got 8 times 7 times 6 all the way down to 1. On the bottom we have 3 factorial, 3 times 2 times 1, and we're also timesing by 5 factorial, so 5 down to 1. So we can actually write that out as 8 factorial over 3 factorial, 5 factorial. So more generally, we can write any combination, NCR, as n factorial over r factorial, n minus r factorial. So notice the n minus r there, the 5 factorial above comes from 8 take away the 3 that we had on the bottom. So that's why we have n minus r factorial. Now we're going to look at combinations and Pascal's triangle. So what is Pascal's triangle? Well, just first to mention, although it has been named after Pascal, who was working in the 17th century, it was known to Indian, Persian and Chinese mathematicians and others centuries earlier, as well as in fact some Europeans leading up to when Pascal was working, but he's the one whose name has got affixed to it in Western culture at least. So what is it? Well, it's an array of numbers which occur in probability and statistics, in combinatorics, which roughly means the mathematics of counting, and in algebraic situations as well. So it pops up all over the place, and the simplest way to develop it is using the each number is the sum of the two numbers above it rule. So if we start with 1, and then I'm going to put noughts either side. We don't write them as part of the triangle, but if we want to have each number as the sum of the two numbers above it, then we need two numbers above. So the next row is 1 and 1, because the left hand one is 0 plus 1, so it's in fact a space plus 1 when we write it out usually, and for the right hand one on that second row we have 1 plus 0 or 1 plus nothing, and so that is of course 1. The next row, now we imagine the noughts going down, we don't write them generally as I said, but we'd have 0 plus 1 is 1, 1 plus 1 is 2, and 1 plus 0 is 1. And then we can just have a look at an actual example. specifically that's a bit more interesting. Not that interesting, but 2 plus 1 is 3. So we'll see on the next row that that's how it's working. The 2 plus 1 gives us the 3, and so on. And the next row we have 1, 4, 6, 4, 1. And the beauty of this is, in terms of what we're looking at the moment, is it eventually gives us all the values for combinations. And that's it written out in combination form. So we can see that if we go to the nth row, then we will have the n minus 1th combination. So on the 4th row we've actually got the 3C0, 3C1, 3C2, 3C3, and so on. Now, the fact that we've got the sum of the numbers above, because this is representing all the different combinations, then we can write that rule using combinations. So we've got 3C2 plus 3C3 equals 4C3, or 3 plus 1 equals 4. And the 4 we can write as 3 plus 1. The 2 we can write as 3 minus 1. So now we can see that we've got all of those written in terms of, if you like, the main number 3. And that means if we generalize, we can say that n plus 1 CR is n CR minus 1 plus n CR. And there's different ways that people write that out, but that's the basic rule written in terms of combinations. And we can show that using the factorial representation of each of the part and some nifty algebra. But there's an informal way of thinking of this, which is quite useful actually. If we have n plus 1 athletes to choose from, let's consider whether Elian, who's one of the athletes, is chosen or not. So, if Elian is chosen, then the rest of the team will be found by choosing r minus 1 players, because we want r players altogether, and we've already got Elian, so we need one less than that. And we need to choose them from the remaining n players. So that is our NCR minus 1. If, however, Elian is not chosen, then the team will be found by choosing all r players from the remaining n. So that would be NCR. So those are the only two possibilities. Elian is either chosen or not. And so we see that the number of possible teams must be the sum of those. So that gives us our n plus 1 CR equals NCR minus 1 plus NCR as before.